Hello and welcome to Quantum IAS. From this lecture onwards, we are going to start our new module, that is solid state physics, devices and electronics. Now, let us see it one by one. So this is the solid state devices and electronics, in which I have categorized this module in basically 4 units or 4 sub-modules, you can say. First one is the crystal structure. Second one is the band theory. Third one is the properties of the solids. Now, understand one thing. In crystal structure that we are going to start today itself, we will be studying the structure of the solid, right? And now the structure of the solid is basically responsible for some of the properties of the solid, right? So making a linkage between the crystal structure and the properties is very important. Now, how we can find the crystal structure, also how we can determine the crystal structure, right? You have studied about the X-ray diffraction, Bragg's law, we have already studied, right? So all these things we will study in detail here. In band theory, again, we will be dealing with the recent model or the latest model of defining how the behavior of electron inside a solid, right? So let's say we have studied about free electron theory in our electricity and magnetism classes, and we have studied about how electron behave inside a conductor. Now we are taking it a more further and we are discussing about how electron behave inside a solid, whether it can be a conductor, a semiconductor, or an insulator, or what we say, dielectric, right? So also in band theory, we will give it a mathematical treatment, right? More like a mathematical treatment, quantum mechanical treatment. Now, let's see in properties, thermal and magnetism. So in thermal properties, we have already studied about the Dave law, right? The T cube law, all those things we have already covered in the thermodynamics. So whatever we have covered, like specific heat of the solid, all these things we have covered in the thermodynamics itself. So let me tell you the things that is important: the thermal properties of solid, specific heat, Dave theory, right? So all these things we have completed. So this we can mark as completed, right? That is all we require to know. Magnetism also we have covered in electricity and magnetism, right? Whatever the things we have discussed in magnetism, like we have discussed paramagnetic substances, ferromagnetic substances, right? Diamagnetism we have discussed, we have hysteresis, right? So all the things we have discussed in great detail. So we are not going to cover the thermal properties and the magnetic properties, right? That should be clear. If we have, if something is left or some weird question is asked in the examination, we will try to address in the question and answer session, right? So we have covered this thing. If you have covered the thermodynamics and electricity and magnetism, you needed to worry about these two topics in the solid state physics and devices. Again, crystal structure is partially of the class 12th chemistry, right? So this is your homework also, right? 12th chemistry, first chapter, right? First chapter, you need to study and study in a detail, right? Detailed study should be required. Now, what else we are going to study? We will focus on superconductivity, right? So these three topics, crystal structure, band theory, and superconductivity, are very, very super important here, right? Now come to the electronics. Right? In electronics, we will more focus on the digital part. Why? Because the analog part is a little bit open-ended. We cannot assume the type of question that can be asked from here, right? So what we will do, what is the strategy will be there, that in analog we will do only the basic stuff, right? If we can answer the question using the basic stuff, that is more than sufficient. Otherwise, cost benefit ratio is not so good here, right? We will complete the digital electronics here, right? So you can see that a very small part of this syllabus we are going to do only the basic stuff. Also, whatever the type of question that is asked in the previous year questions, right? Whether to solve a differential equation, right, using the electronics, right? All these things will be taken in the class itself, right? So don't worry about that. The most important things here is the crystal structure, band theory, right? Superconductivity, right? And digital electronics, right? So around 90% of the syllabus of this module is very easy to understand as well as to score marks, right? Now, let us move to our the first unit or the first subdivision of the module, that is the crystal structure. In crystal structure, we are going to study about the crystalline solid, right? What are crystalline solid and how they differ from the amorphous, we will study now, but we are going to study about the crystal structure. So let us see one by one. First one is crystalline and amorphous structure of the matter. Here, we need to find out only the basic definitions and differences. They're not asking question on these. This is just for the namesake, you can say, right? Next one is the different crystal system. Right? So in this, we have 7 different crystal system, right? So 7 different crystal system we will study. Also, we will study the 14 Bravis lattice, right? We will see the closed packing, right? CCP, SCP, all these things we will study here. So now the crystal systems and the first 2 topics, the crystalline amorphous structure of matter and different crystal system, are very well written in the 12th chemistry book. So you should give it a read here, there. I will also cover here, but you should read from there also. Right? Also in different crystal system, one thing that is very important and they are asking nowadays, that is a diamond structure. Diamond structure is very important. Almost every good question from this crystal system comes from the diamond structure itself, right? So we will study about the diamond structure also some more little stuffs. Next one is space group. Now this is where we talk about symmetry. And basically they are asking about the rotation symmetry. Also, the 14 Bravis lattice is related to these space group, how we do the symmetry operations, right? So we will see all the symmetry operations here. Now, next we will see the methods of determining the crystal structure. We have 3 methods. We will see all these methods. Next, X-ray diffraction, Bragg's law, right? Scanning, transmission, and electron microscope. We will do only the principal structure, right? And what are the differences between the scanning and transmission electron microscope? Which one is better? Which one is used for what purposes? All these things we will study. Now, the first topic is crystalline and amorphous structure. Now, before getting into the crystalline and amorphous structure, let's understand we are talking about solid, right? What is a solid? We know that we have solid, liquid, and gases, but how we define solid? Is there the definition of solid, or just we talk about the relative terms in with respect to the other forms of matter, other phases of matter? Right? So we know that a solid is a substance that will be in a regular fashion. The atoms will be in a regular fashion. It will have a fixed shape. It will have a fixed size, right? The kinetic energy of the molecule or the atom inside a solid will be just enough so that it vibrate in its own lattice. Rate of diffusion is low. So all these things we study in solid, right? So this is the simplest definition of the solid. You can write on your own also. No one is going to ask you, but again, now solid is defined into two. Crystalline solid, some people say that it is divided into three, right? Monocrystalline and polycrystalline. Here we have single crystal, and another one is monocrystalline. And here we have amorphous. Now, understand one thing. First, we need to get differences between the crystalline and the amorphous. Then we will study about the single and the monocrystalline, right? Now, can we say that only the crystalline structure is important, amorphous is not important? No, we cannot say that, right? Because if you see some of the examples of the amorphous, right, we have like glass, right, rubbers, plastics, right? All these things has its own uses, right? Crystalline, again, we have several things. For example, let's say for polycrystalline, we have different ceramics. Right? Different ceramics we have. Here we have diamond, quartz, mica, right? Now understand one thing. This is very important here. We are here interested in finding out the structure. And structure we can find only when there is something which is repeating. If something is not repeating, we cannot find a structure of that, right? So that's why we are not going to study the amorphous solid here. It is not the part of the course here, right? We are going to study about the crystalline. Again, in crystalline also, we will more focus on the lattice than the structure. I will tell you in some due course of time, because from the physics point of view, the lattice is more important than the structure. Right? What is the difference between both of them? I will just let you know. Now, first, let us see the crystalline solid. So crystalline solid have definite geometrical shape. Amorphous solid, it has irregular shape. You can see that, for example, diamond has a specific shape, right? Sodium chloride has a specific shape, right? Glass, rubber, plastic does not have a specific shape, right? Again, melt at sharp and characteristic temperature, right? Gradually soften over a range of temperature. You can see when you burn plastic, you can see these, right? Cleavage property, right? Newly generated surfaces are plain and smooth. Again, it will cut into two pieces with a regular surface. See, this is taken from the NCERT itself, right? You can read it also. Now, important thing is here that heat of fusion is definite, right? Definite heat of fusion is there. You know what is definite heat of fusion? Do not have definite heat of fusion. Anisotropic in nature. Isotropic in nature, right? Anisotropy and isotropy is basically regarding the physical properties along the every directions. If it is same in every direction, it is isotropic. If it is not same in every direction, it is anisotropic. For example, if we talk about refractive index of a thing, let's say this is a material, right? If in this direction and in this direction and in this direction, the refractive index are same, we can say that it is isotropic in nature, because in all directions the properties are same, right? Long range order, short range order, I guess you can understand this thing. It is also known as true solid. It is also known as pseudo solid or super cooled liquids, right? There's differences. Now again, see, this is about the crystalline solid and amorphous solid. Nothing more than that is required to answer. Here, if we can see here, let me show you something. Can you see the gaps here? Gaps are same, triangular gap. Basically, tetrahedral void is there. If you can see here, right? This gap, this gap, this gap, this gap, right? All are same inside shape. The gaps are same, right? The arrangement is more ordered. You see, so basically it is a single crystal, right? And the periodicity is extended throughout the, so crystalline or just single crystal. So periodicity is throughout the crystal, right? But if you can see in polycrystalline, we cannot find it. For example, here we can find out different reason. Here, this is a different reason, right? Here again, a different reason, right? So in this region, periodicity is same throughout the boundary. In this region also, the periodicity is same throughout the boundary. Here also, the periodicity is same throughout the boundary. But you can see here that it is not throughout the whole crystal. Right? So the periodicity changes, right? It changes with the boundaries. And these boundaries are known as grain boundaries. No need to remember the name. And these are called grains. Right? Small patches of grains, and grains are itself in periodically arranged, but throughout the crystal, we are not going to see the periodic nature, right? But if you see the amorphous here, we cannot find any boundary, right? So this is irregular. It is irregular, right? So it is the complete, you can say, the random arrangement. This is the basic difference between the three. In the crystalline or the single crystal, it is same throughout the crystal. In polycluster, we get to see the chunks of the periodic clusters, or we can say that grains. In amorphous, it is complete random arrangement, right? So I guess this is clear. Okay. Now, important here is to know one more thing: why we are studying this thing. Why the crystal structure is important. Crystal structure is basically important to know the structure of the crystal, and this structure sorry, this structure will tend to the properties. If we know the structure, we can find out some of the properties of the solid, right? So I guess we have completed the crystalline and amorphous structure of solid. Here, you should be careful. Just two things important: the difference between crystalline solid and amorphous solid, and difference between the crystalline solid and polycrystalline. You can get a 10-mark question, nothing more than that is required here. Now, let's take some basic concepts of crystallography, right? So, basic concepts. First and foremost, we should understand what do you mean by a lattice, right? What do we mean by a lattice point and what is structure, right? So let me draw. This is a point. See, these are, let's say, some of the holders that can hold any atom or molecule. Right? Also, you can see that it is in a regular fashion, arranged in a regular manner, right? The distance between this is equal to distance between this is equal to between this, right? It can change, but for now, let us assume this thing, right? This is the. Now, can you see here that each point is repeating itself, right? If we put this point and place over the here, right? Or place over here, or place over here. What you can say? If I am translating these points, right? You know that translation vector, right? We can shift them. We can translate them. So if we are translating these points, there is no changes in the points. Let's say it is extending up to infinite, right? These points are extending up to infinite, both sides. And if you are taking one row at a time or one column at a time, and if shifting it parallelly, it will not make any changes in the system itself, right? So now let us define the lattice point, right? So it is basically the imaginary points. Let's this one is basically a lattice point, right? It is a lattice point, and we can say that lattice point is basically imaginary points arranged in a in such a manner that it gives periodicity to the lattice, right? Periodicity to the lattice. Now, one more concept is here. Like, let's say, if I'm taking this space, right? If I'm taking this space can be simply we call as lattice, or we say it as crystal lattice, right? Or also we in some book you can see that space. And what is it? If you can see, it's just basically the collection of the lattice points, right? So it is basically the collection of these points, right? This is the collection of the lattice points, right? Now, also, it is a geometrical or mathematical construct. It is a geometrical or mathematical construct. It need not to, it is just like said, it is imaginary points. We have already, it is an imaginary points, right? So this is not seen in the reality. In reality, we see atoms and the molecules. It is just a point to show that, right? Now, let me write about the crystal structure, right? So, crystal structure. You will get to know the difference as well. Crystal structure is basically lattice plus basis. Crystal structure is basically lattice plus basis. Now, let me explain what is basis. So, basis, or sometimes we call it motifs, right? So, basis or motifs are basically the actual atoms, molecules, or ions that are seen in a crystal structure, right? Actual atoms, molecules that are seen in a crystal structure, right? We are talking about one unit, right? The basis or motifs are basically one unit. Now, let's say, have you seen, let's say, for example, let me give you, have you seen this type of painting? Mm, let's say this is a painting, right? For this painting to make, what you need two things, right? You need two things, like where you want to arrange these symbols plus the symbol itself, right? So if you can see, if you have seen any such thing like any uh, let's say a sari or a dupatta, right? If you go on shopping, all those things, you can see a pattern over there, right? That will make myself more clear with this diagram. Wait. So here, can you see? This is the motif. Now, if you will see, these looks exactly same. Now, what people do, people make a die of these things and then start pressing it on the cloth, right? And this design will make form, right? Now, this is basically the basis or motif, right? And this complete design, here is the crystal structure, right? And what is the lattice here? This is the lattice. Let's say this is the point. At the gap of a distance, we need to put these symbol or whatever you want to write, right? So this is again, we can understand about the crystal structure, lattice and motif. One more example. This is one more example, right? Let's say this is a group of atom. Let's say this is a group of atom, right? NaCl. Okay, so this can be any atom, or molecule or ion, right? And now we defined these at the lattice point. This is how it should be arranged to give the complete crystal structure, right? So now this is, we will see the Bravis lattice. See, this is the lattice. This is the position where we need to put these structure, put these atom and molecule, right? It can be, it can have different shape. Let's say we can have this shape also, right? So if in this shape, if you put this thing, what you will get? Let's say right. So this is what you will get. Right? If in this lattice, Bravis lattice, if you will put this item, right, an apple with joke, whatever it is, right, you will get this lattice, right? If you put this one, you will get that lattice, right? So I guess the three things should be clear in your mind. What is a lattice, right? It is just a geometrical arrangement. It is just, it is giving you a geometry. It is an imaginary points, right? Next one is basis or motifs. Basis, we will use this in this course. Basis basically the atoms or the molecules or the ions that is being repeated, right? That is being repeated. That is the basis. And the structure, if you combine both of them, right? You combine both of them, lattice plus basis, you will get the crystal structure, right? So we are interested in the lattice itself, right? Because if you study the structure is more required in when you're talking about the chemistry, but still we will see the diamond structure, right? Diamond lattice is not there, right? We will come to these things, how we can see it is lattice or not, how and why it is lattice or not. So I guess this is clear. Again, one more thing, but before that, let's talk about the unit cell. Can talk about it in detail also, but let's, okay. Next one is unit cell. What is a cell, right? We know that when we talk about a cell, we are talking about the very small part, right? Cell is basically what? If you can repeat it, it will give you a complete sense of the crystal, right? Let's say this is, so here you can see, here you can see that if you repeat this, repeat over the lattice, it is very important. How we are repeating it? We are repeating it over the lattice itself, right? One more clarification on lattice I will give you when I will tell you the translational vector. But understand one thing, if you repeat over the lattice, you will get the complete crystal, right? So basically unit cell is the part of the crystal, right? So if you want to define the unit cell, basically the unit cell smallest or the simply building blocks of the crystal, of the crystal, right? What is very important that for example, let's cell is very familiar in biology, so let's take example from there only. So let's say if you have a, let's say, stomach cell or skin cell, right? So the all these skin cell will look like alike, right? So similarly here also, that if you're taking a piece of the crystal and all the properties of this system or structure or the crystal is present in this one, right? How the atoms, the same arrangement is repeated over the crystal, right? Arrangement is repeated over the crystal. If you repeat the unit cell, the arrangement of the unit cell will be repeated over the crystal and you will get the complete crystal, right? So unit cell is the building block of the crystal, the smallest part of the crystal that you can take it from out. Okay, so this is the unit cell. Now, unit cell can be primitive, it can be primitive, or it can be non-primitive. No. What is primitive? Primitive is basically the basic form. What can be the most basic form of a unit cell, right? What can be the most basic of a structure, of a crystal structure? That it contains only one cell, only one lattice point, or only one point, right? So, or the atoms or the molecules should be one only. So here effective lattice is one. How we will see? In non-primitive, effective lattice is greater than one. Now understand one thing. Even a non-primitive cell can be a unit cell, right? Also, it is not always that we choose primitive cell to define a unit cell. We also choose non-primitive cell over the primitive cell, right? If we do have a symmetry operation. So there is no preferential treatment for the primitive over the non-primitive. This is the first thing, right? One more important thing is it contains the smallest volume, right? It contains the smallest volume. Again, right? Effective lattice equals to one means that it will contain only one atom or ion or molecule here. For example, that means I'm writing atoms everywhere, right? When I'm writing atoms, you can assume it at an atom or a group of atom or ions or molecules, whatever you want to imagine, just the whatever the basis we are talking about, basis, right? So atoms are found only at the corners. Atoms are found only at the corners. Here, atoms are found other places plus at corners, right? At corners it will be there, but at other places also it will be there, right? For example, simple cubic structure. Recall class 12 chemistry, right? And let's say face centered cubic structure, right? Uh, for example, let's take a cube first. Okay, leave. Let's assume it's the cube. Okay, let us assume it's a cube. Now, how we can differentiate between a primitive and non-primitive cell? So if it is a primitive cell, then whatever the atoms or molecules will be, it will be at the corner. This is simple cubic structure. Right? All the atoms are at corner, right? And I guess you know this thing. Okay. In here, in face center, at all faces you will have one. One at the back also, here also, and here also, right? Now, if you can recall your past memory of class 12, you can say that each atom contributes 1/8 part. Why 1/8 part? If you can see, this is the circle, right? It is not making circle. Let's assume this is a circle. Okay. And you can see it, this much portion is only available for one cell, right? In 2D, we are seeing this. If you can see the 3D part also, right? It is the 1/8 part, right? 1/8 part, and we have 8 atoms, that is equals to 1 atom, right? So this is only the scenario in case of a primitive cell. But here, it is more than one, like 1/8 into 8, right? Plus face center will have half sharing, right? Half belong to this cube and half belong to the cube next to it. Okay, so it is half into how many? 6, right? So it is what? 1 plus 3, that is 4. So this is basically the difference between the primitive cell as well as the non-primitive cell. The effective lattice point is 1 here. The effective lattice point is greater than 1 there. It is smallest volume, right? You can see here also. If the atoms are present only at the corner, the volume will be smallest. And if we have more atoms, right, the volume will be more. Now, this was about the unit cell, right? So till now we have understood the concept of unit cell, lattice, basis, and structure. What are the differences between them? All these we have seen. Now, one more thing. Let's take 1 2 examples to show. See, try to identify if it is a primitive, it is not a primitive one. All these things are primitive because in 2D it is easy to see. Now let us see in here. Let's take this. Is it a primitive or non-primitive? It is non-primitive. Right? Now, if we need to find out the volume of primitive cell, how we can find out the volume? So, in 2-dimensional unit cell will be a parallelogram. In 2-dimensional unit cell will be what? It will be a parallelogram. Let's say all these things, let's say here it is not looking like parallelogram, but it's a parallelogram. Let's say it is also a parallelogram. The distances are not matching here, that's why it is not saying. But in 2-dimensional unit cell, if all these points are arranged at a regular interval, you can find it will always a parallelogram, right? And for parallelogram, what is the area? So area is basically A cross B. A cross B, right? Now we should deal in 3D because we are here for the 3-dimensional only. So in 3-dimensional, it will be a parallelogram, right? So what should be the area? What should be the area here? Parallelogram, the volume. Right? Let's say this is A vector, this is B vector, right? And one C vector is also there. Let's say it is a B vector. This is, or sorry, let's say it's a C vector, and A vector is above. A vector is above the plane. So the volume will be A dot B cross C, volume of parallelogram, right? This we know also. Same from the mathematics. You can write this is the volume, right? Also, how we can make the unit cell, right? So there is a way, and we call it as a Wigner cell, right? How we can draw here, right? So first step, you need to connect all nearby lattice point, right? If you draw all the near lattice point, then what you need to do? Normal, then draw normal to them, right? Then whatever you get in smallest volume, that is your unit cell. Just one line, it can be asked, or you can try to add, right? This is the beginner set cell, right? Nothing more than that is required, right? Now, one more thing here is required. When you're talking about the unit cell, one thing is very important. We just talk about the parallelepiped, right? So let's talk about the unit cell and lattice parameter. Unit cell and lattice parameter. Now, let's say we have three axes. Let's call it X, this is Y, this is Z. Now understand, it need not to be mutually perpendicular. I'm not assuming it as a mutually perpendicular, but what I am assuming that A is a vector in direction of X. Something like a unit vector, right? Or simply A it is written. A vector, or simply A it is written. Along the Y, let's take it B. And along the Z, let's take it C, right? Angle between B and C, let's take it alpha. Angle between A and B, let's take it gamma, and this take it beta, right? So here we have 6 parameters. Here we are having 6 parameter, and it is what we call as lattice parameter, right? That is A, B, C, alpha, beta, and gamma, right? All these 6 parameter will give the lattice parameter, right? And this gives to 7 crystal structure. This will gives to 7 crystal structure, right? And this 7 crystal structure will give to 14 Bravis lattice, right? So I will system, sorry, 7 crystal system, right? What are they? Let me show you the graph itself. So the 7 crystal system we have. Now, one more thing. Not all values of A, B, C, and alpha, beta, gamma are possible. There are some limitation here, right? And this 7 crystal system will give 14 Bravis lattice. It is also symmetrical in nature. We will see the symmetry and all these things. But first, let us identify what are the 14 Bravis lattice. Okay. The first one here is basically cubic. Right. You see here. When we will call this as cubic. Now understand one thing. Crystal structure can be infinite. There can be a number of crystal structure, but the lattice will be same. Are you getting the lattice? Lattice is basically the fixed point in the space, the imaginary point in the space, right? Whatever you want to fit it there, you can fit it there, right? Where you want to make diamond, you want to make NaCl or KBr, whatever you want to make, just put the atoms or the molecules there at those point. Center of the molecule will coincide with these lattice point, right? But the arrangement of the lattice point will be this only, whatever we are talking about. So this is one when A equals to B equals to C and alpha, beta, gamma at 90 degrees. That means all the crystal axes, that A, B, C were defined as crystal axes. See, all these things basically are crystal axes, should be perpendicular to each other. And here are example like copper, NaCl, CaF2. All these are cubic in lattice structure, right? You can see the example from here. I'm just going to discuss this table. Tetragonal when A equals to B, but B not equals to C. Now understand here, see. In cubic itself, we have three models: simple cubic, body center cubic, and face center cubic, right? Here in simple cubic, all the atoms are arranged at the corner itself. In body center, all the atoms are at the center corners as well as inside the body. In the face, all the corners plus face, right? So if you can see here, this system, it will have three. Cubic system will have three systems. Just note it down. It will have three: body center, okay, just put these things also at once. Yes. So it will have three: simple cubic, right? Body centered and face centered, right? So see, these are the system, right? These are the system, that means shape should be like that. But see here in cubic, say what you are seeing, the arrangement of the atoms are different. That is point are different. So in cubic we have three. In tetragonal we have two. In tetragonal we have two, right? Why two? Why three only? Right? This is what it is. You need there is the explanation of these things also, right? But you have to study in the material science itself, right? That is not the part of our course, right? Whatever is defined the Bravis lattice, just we need to understand and remember those things. Nothing more than that, right? Orthorhombic, we have, so in orthorhombic we have four, right? Rest monoclinic, we have two. Triclinic, we have one only. Trigonal, we have one only. And hexagonal, we have one. Okay. So 1, 1, 2, 3, 5, 9, 12, 14. So this is this in the 14. Right? These are the 14 Bravis lattice. Now understand one thing. Crystal systems are 7 only. This is 7 only. But lattice are 14. Now understand shape. If you can see the shapes A, B, C, the combination of A, B, C and alpha, beta and gamma, these are giving you the 7 crystal system. That is important. Now this is your homework to learn all these, right? You need to remember and learn all these things. That is very important. So we have done the unit cell. Okay. Now the next point in the syllabus is regarding the space group, right? And for studying the space group, we need to understand several symmetric operations. We will come to the crystal system once again. Don't worry. We will see how the packings are there, right? But for that, first we need to understand the some symmetry operations, right? So let us write the symmetry operations. Now this is important to know the symmetry operations. Why? Because in UPSC they have asked, right? I guess mm, let me check. Yes, in 13 they have asked a crystal plane. No, not 13, sorry. Yes, in 15 they have asked for 10 marks. Show that any arbitrary rotation axis is not permitted in crystal lattice, right? That means the rotation cannot be of any type. Rotation cannot be of our chosen frame, right? What does it means? We will see these things. So first, what are symmetry operations? What is the symmetry? Right? Symmetry operations are basically those mathematical or geometrical operation that makes the object to coincide with its previous self after the operation. That is self coincidence, right? Self coincidence, you can say. That is, let's say, for example, let's take one example. I'm not able to make this. This is a square. Okay. Let's copy and paste it in. Right? Now, what I'm trying to do, I will just rotate it by 90 degrees. See this. $90. Can you find any changes? No. Again, 90. Right? Any changes? No. Why? Because it is self-coinciding with each other. If you put it here, it will coincide with itself only. Right? So this is basically what we know as symmetry operations, right? It should be coincide with itself only. Otherwise, it will not count it as the symmetry operation, right? So how many type of symmetry operations are there? Symmetry operation, right? And this is also called space group. This is called space group. It is of two type. One, translation plus reflection plus rotation plus inversion, right? And all these three are basically called point group. All these basically are called point group, right? Now understand, see the differences here, right? What is a point group and what is a space group? Space group means basically all the symmetry operations of a crystal, that is known as space group. And point group is basically all these things: reflection, rotation, and inversion. We will see these things one by one, right? So they are also called as non-translational symmetry. Non-translational symmetry, right? Understand these factual information, then we will discuss about the translation and reflection and rotation. Sorry, translation and rotation is very important here. We can have symmetry operation of two types. One is translational and another one is non-translational, right? The combination of both is known as complete symmetry operation or the space group. Space group is what? Why we are saying it as space group, I will let you know. Translational plus non-translational symmetry. Translational plus non-translational symmetry, right? It is basically called space group. Now, one thing important to notice here, that we have around 230 distinct space group. In 3D way we're talking about, we have around 230 distinct space groups, right? And one very interesting point about this, that all these space group, all these operation, right? If you do all these operation, we will end up what we have studied at 14 Bravis lattice, right? 14 Bravis lattice. That means, understand this thing. It is very important to understand. Let's say if you have a solid, right? This is a solid, right? What you will do? You will do the symmetry operation over here, right? You will do the translation, you will do the rotation, you will do the reflection, you will do the inversion. There are 230 different ways of doing all these things, right? Different type of rotational axes are there, different type of inversion reflection are there. But what is important there, that the lattice that suffer, that withstand all these symmetry operation, that is compatible with all these symmetry operation, end up in 14 Bravis lattice, right? So what we can say, that the 14 Bravis lattice are the only possible lattice that can sustain the symmetry operation or the group of space group, all the space group, right? So they are permissible or compatible with these operations, right? So this is what you need to know about the space group. Now, two things is very important: translation and rotation. Even reflection is important, but reflection is not so important. So point group and translation group, right? What our space group, right? We will do two: rotational and translational, reflection and inversion. We will see. So first start with the reflection. In reflection symmetry, we need to just see that there should be a mirror plane, right? let's say we have a sphere like that, right? And if we can have a plane like that, sorry, yes, a plane like that, what you can say, this is, this portion is exactly same as the previous one, right? This one is exactly same as the this one. It will act as a mirror, right? So this is basically about the mirror symmetry. The upper portion is equal to the lower portion, right? It's a two-sided meeting. The left hand side is equal to the right hand side. This is the simple meaning is that only. For example, uh, let's take a body center cube. Right now, if you have atoms here, here, right? Let's say, and one at the middle. Now, if you make a plane such that like it passes through the middle of this one, then you can say that this one is the mirror image of this side, and the left side is mirror image of the right hand side, right? This is basically about the reflection symmetry, right? There can be a number of reflection symmetry, and one thing is very important, that the invariant points are those which lie on the mirror plane. Nothing more than that is required, right? What are the invariant point? Invariant point, that means those point which will not change from this operation, right? So whatever the points, let's say if you have any point here on this mirror, this plane, it will not change at all, right? This is all about the rotation, right? No need to study more than that. Now, the second one is inversion. See why I'm discussing these things, because you can get a question on the space group, right? And if you get a theoretical question, you need to write 2-3 lines about these things. Now, understand what is inversion symmetry. Let us take again this one. Leave it. See, from if this is the point of inversion, okay, this is basically the point of inversion. From here, we are measuring the, seeing the thing, or we are applying the symmetry inverse. Sorry, symmetry operation. If this is the point of inversion, right, this point will remain invariant. This is one thing for sure. If you are applying from invariant, means that will not change, right? What is important here to note, that if at a r distance you are seeing one thing, again, this is the, this is minus r, you are finding the same thing, right? So this inversion is very important when you are writing, when you are seeing an object which has the reciprocal, or which have the negative vector, which both of them they are same, right? So and it is denoted by 1 bar, right? Now, are you getting these things, right? Simply, it is mean that it is the point of inversion. If you're getting something over here, right, which is at a r distance, and if it is a point of inversion, then you will get same thing at minus r. Simple like that, right? This is basically the inversion symmetry, right? And all these are what? Point symmetry. Sorry, point group. Okay, now next one is translation. It is very important. Translation is one of the property that basically defines the lattice, right? Now, we will see some. Okay, this is convenient. Now, if you can see here, okay,